All right. Good afternoon. Got some new camera angles this week. And so this week we're going to go over the Krebs cycle in plants because it's cool. Cool as fuck. I hope everyone's had a tremendous week. Accidentally typed the word wave over on Instagram. I meant to write the little emoji and have it come up, but I got there eventually. We've got a few people over there already. How you doing? Go to the chat. Yeah, so we're going to talk about the Krebs cycle today, micro machines. How nitrogen feeds the tiny turbines that power your plants, power all living things as a matter of fact. Just having some epic rain come down outside too, so hopefully that doesn't interfere with the stream too much. Just responding to some comments over on YouTube. Yeah, so it's super cool that there's basically these little water turbines that power plant cells. So little rotary machines that are powered by amino acids, peptides. They're like basically little Iron Man arc reactors on a microscopic level. And what you feed them sort of can spur this process along, so it can stimulate the Krebs cycle. So we're going to go into it a bit. We're going to sort of get deep into the Krebs cycle, the energy system behind the metabolism that generates ATP, which we spoke about last week. So what I'll do is, see if I can't share that picture, I believe it is. Yes. Right. The Krebs cycle. Oops. There we go. So when we spoke about the hydrogen ions being generated last week, this is effectively the process by which they are generated. See if I can't, yeah, that's shown up on Instagram a little bit better. Simultaneous lives is a challenge. Right, so ATP is the energy currency, and without it, nothing grows. We spoke about that last week. And BRICS is a reflection of ATP output. So basically how well functioning the metabolism is. So, you know, more sugar and dissolved solids present. Better, more well functioning metabolism. But ATP doesn't just appear by itself, it is part of a cycle. And part one is the Krebs cycle, and then part two is the electron transport chain. So together, those are the sort of machines that are behind the machines. And so what feeds this Krebs engine? What feeds into that is amino acids, peptides, sugars, fatty acids. These are all things that are converted into acetyl-CoA. So the output from that system, once the carbon is liberated from those, is carbon, so CO2, that sort of gets liberated basically as a waste product, and your hydrogen ions, so your NADH and your FADH2. So I believe I've got a image showing that one. Oops, that's the wrong one. That one there. Right. So your acetyl-CoA, this is what you effectively get from the breakdown of those other things, so your amino acids, peptides, sugars, etc. They feed into the Krebs cycle. CO2 is liberated, like I said. The hydrogen ions go to the electron transport chain, and it's used to generate your ATP. So that's where, when we talk about stimulating the ATP system, what feeds into the Krebs cycle effectively stimulates that system, which then subsequently stimulates bricks. So amino acids don't just feed growth, they become energy effectively. They're sort of assimilated in a way that once the carbon is cleaved, it's sort of a net benefit. And so, as we spoke about last week, once those hydrogen ions, so your NADH, your FADH2, head to the electron transport chain, the electron transport chain pumps protons. It builds pressure. And that is what effectively powers that water wheel we're talking about, which is the final turbine, which generates your ATP. So your ATP synthase spins, and that is how you generate your ATP. All right. So that's where it's born. That's the actual power grid. That is the arc reactor. And that is powering everything. It's inside the fungi, it's inside the bacteria, it's inside plants, it's inside you, it's inside tardigrades. So there's little water bears wandering around. It's powering them too, powers everything. And so why do nitrates and some synthetics sort of bog this system down? Well, as we sort of spoke about last week as well, there's a conversion process that needs to be undertaken for those things to be utilized by the plant. That uses energy. That energy comes from the ATP system. All right. So now see if I use that diagram correctly. Where are you? That one. Right. So for the plant to effectively utilize it in the Krebs cycle, it has to take the nitrate, it has to convert that down to nitrite, convert that to ammonium, then deaminate that into stuff that can be used in the acetyl-CoA cycle. So effectively convert that to aminos. So that is an energy intensive system. So the plant wants to effectively get aminos from it, but to get that, it's got to expend energy to convert that over. So yes, readily absorbed, readily makes it into the plant. Once inside the plant, that is effectively the result that those sorts of compounds have on the system. And so that's just one example there, and one example of sort of the flow through of conversion processes that happen there. And that is something that certainly doesn't stimulate the Krebs cycle, because for it to effectively be utilized within that cycle to generate ATP, it's got to go through a multi-step process, and that process costs it energy. So this is where the source of nutrition that you feed your plants really does make an enormous difference. Because say if you're getting all or most of your nitrogen from an amino source directly without the added ammonia and nitrogen, nitrates and things like that, then that system isn't taking a hit all the time. So it's not sort of just woo-woo hippie stuff. It's kind of like there is some scientific basis for this within the biology system. Not to mention that, as mentioned, this same system runs in the organisms that run in your living soil. So if you're feeding foods that stimulate the Krebs cycle in the microbes in your soil, so they have more ATP, therefore more energy, therefore can do more, and you're also stimulating the metabolism of your plant through the Krebs cycle, not to mention that some of these amino acids have direct signaling benefits to the plant. So they actually produce a metabolic and biochemical response. But just even within the Krebs cycle, it's not taking a hit from that. So it might be a little bit slower burn, maybe. Amino acids are generally very, very well absorbed. In fact, there's specific channels for those to be absorbed. But it's a method of doing it that doesn't actually take a hit to that system. And that's how the Brix level ends up higher. And it's something that you realistically can't get around when you're using synthetics. So at every step of that process, there is a cost to your ATP. It's like refining your fuel mid-flight. You're burning energy just to make your fuel usable. So amino acids walk right through the door. You can effectively sort of think of it. Ammonium knocks. Nitrate shows up with baggage and it needs a translator. And a lot of your other synthetics like monopotassium phosphate may not act in that same pathway in terms of the reduction down to aminos, but they hit the system in a similar way. So if you're using a combined blend of all of those things, you can sort of see how you might grow a lot of biomass, but how that would be low in Brix and subsequently lower in the secondary compounds, which are more generated from plants that have a better functioning metabolism. G'day, Warriganj. Hello to everyone over on Instagram. I can see you all over on the other monitor today, which is actually pretty cool. All right. So then we get to the trap of, because, you know, the word amino is thrown around a lot. When I talk about an amino acid-based fertilizer, I'm talking about something like the aquamarine, which is predominantly composed of raw amino acids. So and phosphoproteins, phospholipids, things of that sort. So sort of the raw elements, which has to, in that Krebs cycle, be cleaved. So they will effectively liberate the CO2 from all of that sort of stuff. So a phospholipid, you know, fatty acid, right? Phosphoprotein, phosphorus bonded to an amino acid. So that stimulates the Krebs cycle. Both of those do, as a matter of fact, because both of the byproducts of those are usable in the Krebs cycle. And then the phosphorus is usable in the generation of ATP. In the case of amino nitrogen, The aminos directly stimulate the Krebs cycle because they're able to be rapidly uptaken into that. And so that stimulates ATP. So then we get to the trap of amino chelated salts, which is one of the most commonly sort of chucked around sort of ones. They're quite cost effective, I guess, to formulate into things, but they're effectively a synthetic salt bonded to an amino. So there's a covalent bond there, usually between something like glycine. And so, like, how can I put it? If I get a glass of water and I put a tablespoon of salt in it, and then I get a glass of water and I put a tablespoon of sugar in it, does the sugar negate the salt, or do you just have, sweet, sugary water? Right. Now, that's ultra simplistic, but when you get to the Krebs cycle, effectively, that's what you're talking about. So, yes, you're providing, and in this case, there's normally only one amino acid bonded to it. It's normally something like glycine. So, yes, you've got glycine, but you've still got to go through that conversion process. So, say if it's calcium nitrate or something like that, the salty portion of it still has to go through the conversion. The nitrate still has to go through that nitrate to nitrite, through that whole process down to being able to be utilized within the Krebs cycle. So yes, that glycine is probably of benefit, but certainly not enough to offset all of the other stuff. And you wouldn't necessarily say that it's stimulatory to the system. At best, it would be sort of maybe like a net, like a 1-1, maybe not a plus minus, maybe a plus minus. It sort of depends on the situation. That's in the case of a covalently bonded one. In cases where you've just simply got salts that are mixed with something like soy amino acids or a plant-based amino acid, that's a much more simple formulation. Still doesn't necessarily offset anything. So you've still got to, whatever the synthetic is that's being provided, you can pretty well be assured is going to affect the energy system of the plant in some way. So if we go that one. So there's a calcium amino acid chelate there. So you get to the first step, the calcium is used, obviously, and then the amino step goes to the next stage, converts on through deamination. Once that's at that point, then it can feed into the acetyl CoA and then stimulate the Krebs cycle. So some people might look and think, yeah, cool, it gets both. But there's no such thing as a biological free lunch. So whatever the plant has to do to sort of convert things over is not a biologically neutral process. It does cost energy. Whereas there's other forms that you can feed that are a biological net win because they stimulate the system as well as provide effectively what it's trying to get to. So it's trying to get to amino acids and you just provide them. Fatty acids and things like that are normally the byproducts of microbial breakdown. If you provide those in sort of, a high quality form, preferably something that's not oxidized to heck and is actually capable of being broken down and utilized quickly, then it still goes through that pathway just at a very rapid process. So yeah, that's a lot of things basically on the market because a raw amino acid product is a quite expensive thing to sort of formulate correctly. Liquid versions of them can degrade over time, especially organic amino acids, and then you've got to look at things like preservatives. Yeah, so a full spectrum amino acid product is sort of less common. What you often find is synthetically bonded aminos. And so, yep, still pays the cost of processing the salt, and the amino often isn't enough to offset the drag. So it's like sticking electrolytes in your Red Bull and just going, okay, yep, cool, that's healthy. So as we mentioned before, the Krebs cycle also powers the ATP system in microbes. My favorite little critter, the tardigrade. And so they also consume amino acids directly. Um, and that will help spur their metabolism, which helps break down and hydrolyze other proteins within the soil into usable forms. So they share the buffet, but they also prime the system to sort of produce more of the compounds which the plant prefers. So yeah, a net benefit, because it's all preferential food. In the case of the amino acids, it's preferential in terms of the nitrogen hierarchy. So yeast assimilable nitrogen, it's right up there. It's certainly above ammonium. So stimulates them, stimulates the whole Krebs cycle within both sets class of organisms, so both your plants and your microbes, and that then sort of stimulates the entire system. So if you use care and diligence, you can sort of eliminate some of the stuff that'll cause a hit to that system at the same time as using things that work in the direction of what you want, but simultaneously stimulate it as well. So I did. There's someone on Instagram asking what ATP is. So that's adenosine triphosphate. I did a live last week on that. That's up on the YouTube. It's probably best to maybe just catch a few minutes of that one. But effectively, it's the underlying energy system that powers the metabolism of all living things. And the Krebs cycle that we're talking about today is what feeds that system. So you can effectively think of two turbines, one sort of feeding off the other one. So yeah, your Krebs cycle is sort of the first step in the process that generates the ions that power the electron transport chain. And that proton pump is what makes adenosine triphosphate. So the best fuel for that is your amino acids, peptides, fatty acids, things that can actually be used within that process. And your nitrate heavy synthetics, things of that nature, are stuff that is going to cost the plant energy to convert. Amino acid bonded salts look, maybe a little bit better than just plain salts, but at the same time, it is effectively, at the end of the day, biologically still synthetically based for the most part. So to stimulate that system, get higher ATP and therefore higher Brix, and also stimulate that system within the food web, you want to feed stuff that's actually going to spur that along, not bring along baggage. All right. I've probably bored everyone enough, but does anyone have any questions? There's a few people still over on Instagram I can see, and we've got a couple on the other platforms. So we sort of started with Brix, then we got to ATP. Now we're sort of talking about what stimulates kind of that system. As much as this stuff might be sort of a bit of a strange concept for a lot of people, it is something that kind of pays to understand in a way, because when people talk about stimulating plants and why some of these ingredients have validity, without sort of getting into the, I guess, undercurrent of how that stuff's actually working, it's all just kind of hard to discern any fact from fiction. And then it's hard to check studies and things and see what's actually the scientific consensus on stuff. Anecdotal evidence is great, but at the same time, it is just, the kind of lowest rung um, in terms of scientific credibility. Yeah, some people saying there it's like a never-ending process. It just gets deeper and deeper because the further you sort of get to the little metabolic pathways and things that are happening not just within the plant but also within interactions with microbes and even within microbe groups themselves, it's infinitely fascinating and um, yeah, it's an entire universe. But at the same time, there is more and more understood about it all the time. And so we can utilize that better knowledge, I think, to, to sort of try and advance stuff in a way. As much as sort of, hydroponics likes to paint itself as being the latest tech, it was sort of, the concept comes from 1945. Like it's old as the hills, bro. Look at a 1945 model car or a machine or a tractor or something like that. And then realize that, there's been, you know, probably 10 to 15% innovation within that space realistically over the last, like, however long. So it's not that it's necessarily the best way to do it, I think. It really comes from sort of a relic time when reductive sort of, if you can reduce everything down to the smallest um, set of sort of inputs, then you can sort of distill everything right down. And then the more you try and distill stuff down, the more you find that you can't effectively distill it all the way down. So then over time, you add more and more things back, right? But they certainly didn't understand a lot of the biological processes all the way back in 1945 that they understand now. In fact, if they did, a lot of the chemicals that were released into the environment and are still around now probably wouldn't be there. So yeah, I love, I guess, biological approaches to this stuff. That's where it's at. Because as cool as it is to sort of, get into sort of puritanical approaches to all this sort of stuff, at the end of the day, efficacy is where it's at. Um, that's where the rubber meets the road. And if you can get a better result with something that kind of, works in a different way and just happens to be a bit easier and more sustainable, then that's sick. So I guess what I'm trying to do by explaining some of this sort of inner biology behind the plant is sort of give you some reasons for why you would sort of look at that, not just some sort of intangible, well, it's better, because um, if you can sort of understand some of the science behind some of that stuff, then even in a smaller level, um, it sort of adds to some of the understanding as to why you would want to use some of that stuff, why it's worth the hassle sometimes. Oh, there's well, I mean, the formulas and everything are updated continually, but yeah, I don't want to spill any tea, but I've definitely got some things. Soon, the perpetual soon. But what I can say is that that is something that we're this whole process. So the Krebs cycle, ATP, bricks building, all that sort of stuff, is stuff that we've kind of factored into the formulation of things. So trying to factor in how to sort of metabolically tune the plant at the same time as feed it, at the same time as preferably stimulate the soil microbes as well. That's where I really like dry powder formulations, because they let us not have to use preservatives. pack a huge amount of things into one formula, and because it's in a dry powder, it doesn't interfere and break down in a solution form. So you don't end up with just a bunch of sludge sitting in the bottom of a bottle that's probably all reacted and doesn't really work anymore. But the latest versions of Aquamarine and Ocean Potion are already out at the moment anyway. That features the ultra micronized fishbone meal, hydrolyzed fishbone meal. So that's a process that we sort of put together to maximize phospholipids and phosphoproteins. But I'll let you know other stuff as it comes out. What about the Krebs cycle? Does anyone have any questions relating to it? It's cool being able to like go over to here with the monitor too. This is fun. I tried to set it up so I could draw on the iPad, but I couldn't seem to get it to work as a camera. Cool. All right. Well, this will remain up on the YouTube. It sort of uploads a while after the stream ends, but yeah, I'll leave it there. You can go back over it. Hopefully the pictures and stuff that I shared show up on that clearly enough to read. If not, I'll try and share some stuff through the week, either as a post or in stories. Appreciate people turning up, tuning in, dropping out. All right. Catch you next time.